Hey guys, hope you're all doing good and welcome to a new video. So in today's class we will be looking at these topics. So I'll first help you refresh your fundamentals of trigonometry. Then we will look at the basics of vectors, talk about dot product and its physical meaning, and then we will jump into coordinate transformation. Okay, so let's talk about trigonometry, right? So at the end of the day, trigonometry, from most of the examples, doesn't matter where you go to school, primarily at the end of the day the applications are with respect to a triangle. If you have a triangle, how do you compute the sides, how do you compute the angles, right? That's essentially what trigonometry deals with, or at least one of the things it deals with. And you will see that there is always a right angle triangle and there is an angle, right? So then the side that's actually opposite to the right angle triangle, that's the hypotenuse. So the other side, which is used to make the angle, right, that's what you call as the adjacent side. I'm pretty sure most of you know this, but one thing that I always try to do is imagine a crocodile, right? So imagine a crocodile that has its mouth open. My drawing of the crocodile is pretty bad. It looks like a lizard, but that's fine, right? So this is theta. Okay, so the upper jaw of the crocodile is the hypotenuse and the lower jaw is the adjacent side, right? Remember that the opposite side is this, right? So the opposite side is essentially where you have no parts of the crocodile, it's just the air, right? It's how big the jaw opens. Okay, so now once you have this, there are so many things that you can calculate. So the first thing that we all know is that we know that cos of theta, right? Cos of theta is what? It's adjacent side by hypotenuse. In other words, the length of the adjacent side is nothing but h cos theta. And if you look at sin theta is nothing but opposite by hypotenuse. So the length of the opposite side is h times sin theta. So this is actually a great thing. What I can then do is I can use these two formulas to compute the adjacent side and opposite. So let's take a look at a few iterations here. So the first thing is I want to draw a triangle like this, and I'm going to say that this is theta. Okay, so we know that this is the adjacent side, right? Again, going with the crocodile example, and this is the hypotenuse, and this would be the opposite side. So the thing is, the length of the adjacent side is always going to be equal to h cos theta, and the length of the opposite side will always be h sin theta. The reason why I'm stressing on this so much is that you won't believe the number of people that have confusion with this concept. And at the end of the day, if you're able to get a firm hold of this concept, you can actually go a long way in learning mechanics, fluid mechanics, dynamics, and whatnot, right? Because at the end of the day, what we are essentially doing is we are calculating components, right, which at this point might not be super clear to you, right? So now let me come with a trickier example, right? So what if you have something like this, and this angle is alpha? So what is the length of this, right? And let us call this as L. Okay, well, this length is going to be L cos alpha. Okay, so essentially the thing that you can think of is, imagine that there's a light source here. If there's a light source here, and if the light actually falls, the length would essentially be the length of the shadow, right? And this is L cos alpha, and the opposite side would be L sin alpha. So similarly, let's take one last example. Okay, I promise. So if you have an example like this, where this is gamma and this is equal to r, right? Maybe I'll do capital R. So what is this length going to be? You should be able to tell me instantaneously. This should be r cos gamma, and this length should be capital R sin gamma. Okay, so make sure that you're comfortable with this, right? This is very, very important. And why am I talking about only these two components? Well, if you know these two components, right, the length of the hypotenuse is very simple. It's just Pythagoras theorem, right? It's r square sin square gamma plus r square cos square gamma, and if you simplify this, it's essentially going to be r square into sin square gamma plus cos square gamma. Sin square gamma plus cos square gamma is 1, so you have square root of r square into 1. That's going to be equal to square root of r square, which is going to be r, right? So fairly roundabout way to basically calculate the length of the resultant is r, right? But that's the whole point. The reason why we remember components is calculating the resultant is so much easier. You just have to remember the Pythagoras theorem, which I'm pretty sure most of you, or in fact all of you, know, right? Especially if you're watching this course. Alright, so let me clean up this mess a little bit. Okay, so let's go back here. So I think that's essentially the basics of trigonometry that I want to talk about. I hope you guys are comfortable with this. If you want, feel free to think about what tan theta would be. Again, you should be able to calculate that. Okay, so now coming back here, the second thing that I want to talk about is basics of vectors. Okay, so vectors are quantities that have direction and magnitude. Okay, so if you take temperature, right? If you take temperature, and what I'm going to do is I'm going to take a room. So this is a simple room that I have. Okay, so at each and every point in space, for example, say that in the top there is a ceiling fan, right? That's a very bad looking fan, right? And say that you're standing here. Okay, so the fan is going to hopefully keep you a bit cool. So the temperature maybe somewhere here is going to be lower, right? The temperature at that point is lower, whereas the temperature maybe somewhere away from the fan, maybe at this point the temperature could be higher, right? So at the end of the day, temperature just depends on that location. There is just one value. Now from this point, if you are at this point, right, say that you are a person who is standing here, you will see that you're not cool enough, right? That's it. That because you're feeling that you're warm, right? But there is no direction sense to it, correct? If you close your eyes and if you kind of in the same spot just turn around, you will still feel the same lack of cool air there, right? And that's essentially what a scalar quantity is. What's a vector quantity? Well, a vector quantity is a quantity that has magnitude and direction. Okay, a great example for this is displacement. Okay, for example, if I'm asking you to go from here, for example, say that I have a planet, okay, right, and this is the center of the planet, and I have a control center at this point. Okay, now what I'm doing is I'm telling you that, hey, this is my x-axis and this is my y-axis, and this distance is the radius of the planet. Okay, so if I tell you that, okay, you start from the center of the planet. Okay, so center point is the starting point, and for the ending point I'm saying that, hey, just travel a distance equal to the radius of the planet. In that case, I can end up anywhere. I can go here, I can go here, I can go here, right? And essentially there are infinite combinations for me. But what happens if I tell you that, hey, start from the center of the planet but travel along x-axis? This is what you would call as a vector quantity. There is a magnitude component, which is the distance that you're traveling, which is r meters, but in addition to that there is a direction, right, which is what you call as a vector quantity. Okay, so then the next point that we want to talk about is how vectors are represented. So for example, if you take velocity, the velocity vector is represented with an arrow on top, right? So this is what you would call as velocity vector. Okay, so I'm assuming most of you already know this. Remember, I'm not trying to teach you vector calculus from the start. I'm just trying to help you refresh the concepts that you might have learned in the past. So now let's take the coordinate system, x-axis and y-axis. The next thing that we're going to learn is something called as unit vectors. So unit vectors are essentially vectors that go along your coordinate system. So along x-axis, it's a common practice to say that the vector is called as I vector, and along y-axis it's called as the j vector. Okay, so it's essentially a direction. It's a vector quantity, but the vector has a magnitude of 1. Okay, is it 1 meter or is it 1 millimeter? Essentially unitless. It has only direction, right? It just says, hey, go along x by 1 units. The actual unit depends upon the value that gets multiplied. So for example, if I say I vector, that just means x-axis. But say that I want to travel 5 meters, right? So let us say the displacement is 5 meters. Okay, then d times I vector would essentially be the vector quantity, right? So where d is 5 and I vector is the direction. So the vector v is equal to 5 times I, which means I'm traveling 5 units, which is 5 meters along the x-axis, and this is what you would call as a vector quantity. Okay, and this is where we are slowly going to start applying the rules of trigonometry, right? So if you have a vector like this, well, it has two components, right? It has an horizontal component and a vertical component. So what is going to be the horizontal component? The horizontal component is essentially v vector cos, if this angle is theta, cos theta times I vector, okay? And what about this guy? What about the y component? Well, it's v vector sine theta times j vector. Now notice that I'm essentially applying the same trigonometric concepts that we used before, and that's why I mentioned that those concepts are very, very important, because when you're dealing with vectors, which is everywhere in engineering, you need to be able to apply the same concepts again and again. So this is how you basically calculate the components of a vector. So now let's define vector multiplication, and primarily let's define dot product. Okay, so what's a dot product? So if I take a vector A and if I dot it with vector B, that's equal to magnitude of vector A and magnitude of vector B multiplied by cos of the angle between the two vectors. So if I have a vector like this A vector, and if I have a vector like this B vector, and the angle is alpha. So what is the right hand side? Well, let's just rearrange this, right? So this is A vector cos alpha times B vector. So what does magnitude of A vector mean? Well, the magnitude of A vector is very simple. So if I take a vector which is A1 I vector plus A2 j vector, the magnitude of A vector is equal to square root of A1 square plus A2 square. So the magnitude of the vector represents the length of the vector, right? And that kind of makes a lot of sense if you're talking about displacement. If you're taking the displacement vector, the magnitude of the displacement vector is the amount that you are displacing in meters or kilometers or centimeters, right? But if you have a force vector, the magnitude of the force vector is essentially the value of force that you apply. Okay, I hope that makes sense. So imagine that A vector is essentially the force. Okay, so in other words, I'll just call this as F vector, and then I have another vector called D vector. So D vector is my displacement vector, right? So you can kind of think of this as, alright, I have an object like this, right? I have a box like this. I am trying to move that object by applying a force in this direction, and I'm moving it in this direction by d units or whatever, right? And the angle is alpha. So when I do F vector dot D vector, I get the magnitude of F vector, the magnitude of D vector times cos alpha. Now just rearrange this a little bit. So if we take F vector cos alpha times D vector, now what is F cos alpha? Well, that's the component of force along this direction, right? So in other words, this is nothing but the component of force, or it's the magnitude of force along the direction of displacement. Okay, I hope that makes sense. So in other words, this is kind of giving me a small f. I'm going to call it a small f. Small f times d. I have force times displacement, which is nothing but the work done. Okay, so dot products are really awesome because it helps me calculate work done in a particular direction, right? And if you think about it, for example, if you have a 3D coordinate system like this, you know, x, y, and z, and say that I take a box like this, right? Say that I'm taking it in a very complex direction, okay, something like this, and I'm applying a force like this, right? And you can kind of immediately see that by applying a force like this, it's going to be very hard for me to take the object here. And especially if this object is constrained to move, for example, if it's a link, right? If it's a link or if it's a joint which can move only in this direction, applying a force like this is not going to make me move it. And if you kind of want to understand this in a better way, think of a door. So let me try my best to draw a door, right? So this is a door, okay? And this is the door knob, and this is the hinge. So the constraint is that the model rotates about this axis, right? So this is a door. Now if you want to try to open the door, if you would apply the force like this, correct? And that would essentially displace the door in the radial direction. So that's how you make the work happen, correct? Now for the same doorknob, what happens if you do the work like this? If you put the force like this, you might break the doorknob, but you're not going to get work done, right? And that kind of shows up in the math by the cos angle, right? So cos of 90 is what? 0. So if your displacement and forces are 90 degrees inclined, then it doesn't matter how much force you put, you will end up maybe breaking the doorknob, but you will not be able to move it. So that's why dot products are very, very important. And I hope now you know how to actually compute the dot product. So a few rules about a dot product. So what is the dot product of I vector dot I vector? Well, it's nothing but magnitude of I vector, magnitude of j vector, and cos of the angle between I vector and I vector, which is 0, right? Cos 0 is 1, the magnitude of I vector is 1, and magnitude of j vector is 1. So in other words, I vector dot I vector is 1, and similarly I vector dot j vector is going to be 0, right? So these are important concepts that you need to remember. Alright, so that being said, now let's take a look at coordinate transformation. For example, let us say that I have a coordinate system like this, x-axis and y-axis. And now what I'm going to do is I'll say that I have a vector called as a vector. Okay, I'm just going to call this as a vector. Okay, now what I'm going to do is I'm going to think of another coordinate system which I'm going to call as x1 and y1. Okay, and I'm going to say that the coordinate system is rotated by an angle of theta. So this would be theta and this would be theta as well. The other thing that I need to define are my unit vectors. So what I'm going to do is along the xy coordinate system, my unit vectors are going to be I vector and j vector, and along my x1 y1 coordinate system, my unit vector is going to be I1 vector and j1 vector. So alright, so now let me define a vector in the xy coordinate system. I'm going to say that a vector is a times I vector plus b times j vector. Okay, so for the sake of clarity, what I'm going to do is I'm going to draw the xy coordinate system separately, and I'm going to represent the a vector there. Okay, so what is a? Well, a is the component of the vector a along the x-axis, and b is the component along the y-axis, and that's why a vector is equal to ai vector plus bj vector. So in x1 y1 coordinate system, right, I kind of drew it like this, right? It's inclined x1 y1, and my a vector is kind of maybe closer to the x1 axis, right? So here this one would be a1, right? The magnitude or the component would be of different length, and this length would be b1. Okay, so in the x1 y1 coordinate system, a vector is going to be a1 I1 vector plus b1 j1 vector. Okay, but here's the interesting thing, right? At the end of the day, they are both a vectors, but in one coordinate system it has a particular component, and in the other coordinate system it has a different component. Now the question we need to ask is, how do I go from one component to the other component? Well, it's very simple. So what I'm going to do is I'm going to take the first equation. Okay, I'm going to say a vector is equal to ai vector plus bj vector. Okay, and what I'm going to do is I'm going to multiply this with I1 vector on both sides. So a vector dot I1 vector is equal to a vector times I vector dot I1 vector plus b times j vector dot I1 vector. I made a small mistake. This is not a vector, it's just a component of a. Alright, so what is I vector dot I1? We know that I vector is here, I1 is here, right? So this is going to be magnitude of I vector times magnitude of I1 vector cos theta plus b times, so what's the angle between j vector and I1 vector, right? So that's a bit tricky, you might not be able to see this, so let me just draw that separately. So this is j vector, okay, and this is going to be I vector. Okay, I and j have an angle of 90 degrees in between them. Now this is I1 vector, right? So this is I1 vector and this is an angle of theta, correct? So what should this angle be? Well, this should be 90 minus theta. So in other words, if I'm trying to compute the dot product, it's very simple, right? It's a magnitude of j vector multiplied by magnitude of I1 vector cos 90 minus theta. So what is a vector dot I1? Well, that's going to be a1, correct? So a1 is going to be a times the magnitude of all the unit vectors are always going to be 1. So this this and this and this, all of them are 1. So I'm left with A cos theta plus B cos 90 minus theta. Similarly, so if I simplify this one more step, I will get that A1 is equal to A cos theta plus B sin theta, right? Because cos of 90 minus theta is sin theta, and this is what you call as coordinate transformation. Think about it. If I know my angle theta, I can use the values of A, B and to compute A1, and that's exactly what I have done here. A and B are the components of vector in the xy coordinate system, and theta is the amount by which the coordinate system is rotated, right? Based on just these 3 information, I can compute the components. I can do a similar exercise. So instead of doing a dot product with I1 vector, if I do a dot product with J1 vector, I would get an expression for B1, and feel free to do that as part of your exercise. Okay, and this is what you would call as coordinate transformation. The reason why this is so important in aerodynamics is when you are measuring aerodynamics forces, it's always with respect to one coordinate system. In one of the upcoming videos, I will be deriving the force equations for an airfoil, where the coordinate system will be centered based upon the chord of the airfoil. Whereas when you're trying to estimate the aerodynamic forces, that coordinate system will be placed on the surface of the airfoil, right? So you need to be able to calculate the net aerodynamic forces based upon the chord based coordinate system at the end of the day, right? And that is where coordinate transformations are very, very useful. Alright, in addition to this, if you come from a solid mechanics background, or if you're interested in solid mechanics or multi-body dynamics, coordinate transformations are used all the time, so that you can convert quantities that are calculated in one coordinate system into quantities that are calculated in a different coordinate system. Okay, so I'm going to show you one more example, but since the video is already too long, I will talk about that in the next video. Thank you so much. Bye.